Hello, everyone, and welcome to today's Ask the Expert webinar on failure analysis of electronic devices. Our experts for today are John Han, Director of Failure Analysis, Vidhu Weerasinghe, Principal Engineer, Wenxin Sun, Manager of Failure Analysis, and Dan Sullivan, Senior Regional Sales Manager. My name is Vivian Ho, and I'm the Marketing Specialist assisting with today's event. Before we get started, I would like to go over a few housekeeping items. All attendees have been muted. However, if you have any additional questions that pop up during the presentation, please submit them in the questions section located in the bottom of your control panel. You may send in your questions at any time during the presentation. Time permitting, we will answer these questions during today's event, or we will follow up with you in the coming week. With the abundance of questions submitted for today's event, we unfortunately will not be able to get to all of the pre-submitted questions during the presentation. For any unanswered questions, the team will send answers out to those questions soon. At the end of the webinar, a survey will pop up on your screen. Your feedback is greatly appreciated and will help us improve our future events. Now I will turn it over to Dan, who will also be moderating today's presentation.
Hello, this is Dan Sullivan. We're going to be talking about failure analysis today and ask the experts. So we have three experts here. So I'm up in the upper left-hand corner. I've been in the Valley since the 80s. Running FA labs or materials analysis labs. And you can see Wenxin there is running our materials lab, our failure analysis lab here in Sunnyvale. Been working for over 10 years in the Valley. John Han is the director of failure analysis, and he sits down in Southern California, along with Vidhu, who's one of our principal engineers, who's working on all kinds of interesting projects. Each of them will be talking during the seminar and answering your questions. If you do have questions, please send them into the questions and we'll get to them at the end. And if we can't get to them at the end, we'll respond with emails later on if there's too many questions. So, sorry, I just went through that slide. John, can you go to the next slide? So EAG has laboratories here in California and across the world. The majority of the FA labs are in Northern California and Southern California. We do have labs in St. Louis that do a lot of chemistry work. We have labs up in the upstate New York that do materials analysis, and down in North Carolina as well. We do have labs in Europe, in Eindhoven and in France, and down in Switzerland now as well as our labs in Asia, including China and Korea and in Japan. Next slide, please. So the group that we're talking about now, the failure analysis group, is in our engineering science division. In engineering science, we wind up doing failure analysis and work with people's products, new products, and through the process. But I believe, John, you're going to talk about this going forward? Oh, I'm sorry. So in our talks here, we're going to talk about failure analysis, but that's only part of engineering science. We also have ATE test, environmental and reliability testing, ESD and latch up, as well as we can design and have built PCB test fixtures. We also do FIB circuit edit, which is involved in doing microsurgery on your ICs in order to correct failures instead of going and doing a full respin. Next slide, please. So we will answer our questions at the end, your questions at the end, and if you have additional questions that go over time, we'll wind up getting back to you via email. So John, I think you're going to take over from here.
Yes, thank you very much, Dan, for the great introduction. And I'd like to thank everyone for joining today. And with all the great interest and questions, there were some that were kind of similar in a way, and some that were very specific. And I got to say, we have a very diverse audience today across many industries and technology sectors. But I think one thing that's common is that everybody's working with some type of electronics. And so hopefully you'll enjoy this presentation and spark some interest, excitement, and hopefully some ideas along the way. So we took all of the questions that you had put into the request during the registration and categorized them in kind of a similar and grouping theme way. And we'll start off with some of the general stuff, and then we'll kind of continue on to some more practical questions. So let's get started. So first, the category of questions is kind of related to general failure analysis. I think many of you were expressed that you're new to the industry. Some of you kind of wanted to know the process flows and some of the engagements and interactions. So starting from the question bubble on the left, I'm new to this industry and would like to learn more about FA. What is the general order of operations to follow and begin a FA investigation? And what is the typical diagnostic process flow you would follow for triaging electrical failures? Where do you start when you're doing FA? How is the decision made on analytical techniques are employed? So we have a couple of basic categories of failure analysis, which we deem electrical failure analysis, or EFA. And then there's a physical failure analysis, or PFA. And the electrical failure analysis is kind of the upper section of this process flow chart on the left. And it's a pretty basic flow chart, but it kind of shows you that there's locations of or feedback loops and be able to reorganize and redefine some of the analysis. So the electrical failure analysis actually starts with things like verifying the failure, whether it be on the bench or on an eval board, maybe an ATE data log, some basic IV characteristics and curve tracing. So that would be falling into some of the electrical failure analysis, or EFA, which would be the initial portions of the work. It also encompasses some of the fault localization techniques, which we'll maybe touch on a little bit later, but these are techniques to isolate the failure down to an XY position so that we can enable the next phase, which would be the physical analysis, the PFA. And this involves a lot of kind of the teardown exercises, deprocessing, cross-sectioning, and some of the advanced imaging to actually image the failure mechanism. So how do we actually start this FA process? There's a lot of kind of the initial questions, and one of the most important things to start off with is the history and background. So, sometimes customers will engage us and ask us for a project, and we'll actually give them some of these initial questions, like what's the sample type, what's the failure mode, and some of the history, like where's the failure origin, failure rate. And all of these actually kind of tell a story. And we always in FA like to get back and try to answer that story with the findings that we have. So starts with some of the gathering of information, failure mode information, background, origin of the failure. And then we start to put together a rough analysis plan in this first phase. And then once we verify the failure through electrical FA, EFA, then we want to see, did we confirm that failure, or are we seeing some symptoms of it that would allow us to utilize some of these fault localization techniques that are more apt for certain types of failure modes and mechanisms. And then from there, it may involve some of this physical analysis a little bit to maybe deconstruct and access certain points to enable the fault localization. So at all these points, we're going to be refining the analysis. So the initial portion would be non-destructive or non-invasive type of measures to look at things internally, whether it be things like acoustic microscopy or X-ray, 2D, CT, 3D X-ray. And then from there, we would go into some of the fault localization. And once we've identified an XY position of the failure, whether it be on the die or whether it be on the package or maybe on a board, then we would need to design the appropriate physical analysis techniques, such as deconstructions, cross-sectioning, deprocessing, and then actually imaging the failure mechanism with the potentially optical inspection or SEM or TEM, something more advanced for the smaller nodes. Then with that failure mechanism, then we would try to tie that conclusion, which would be root cause. And all of this has to kind of fit with the prior history, does it fit with the origin? Does it fit with, some of the things like the failure mode that we initially investigated? Now, determining what type of techniques to use is kind of falls upon the experience of the analyst as well. And based on some of the history, we may actually start to triage some of these techniques. If there's a high failure rate, we may want to utilize some of this quick turn analysis to get some quick answers to either directly identify a failure or indirectly eliminate failures, which could be actually pretty important. So here's a list of a lot of techniques that failure analysis involves, and this is only a partial list. There's about almost 30 tools and techniques here, and we unfortunately will not be covering all of these, but we've kind of grouped them into major categories. So non-destructive testing, which may involve some of the electrical characterization work, and acoustic microscopy and X-ray, and then the fault localization techniques involving some of the laser signal injection microscopy work, microprobing, nanoprobing, or any just kind of electrical characterization work. And then there's a physical analysis that involves maybe some sample prep. We use a variety of different techniques. And again, as an FA provider, we have to have a lot of availability of different types of methods and tools because all of your samples are fairly unique and some are pretty complex. And so the physical analysis may involve on a dye level, maybe deprocessing, some of it maybe cross-sectioning, and others involve some of the ion milling with an argon broad beam, or some of these other mechanical type of testing. And then of course the advanced imaging would involve SEMs, dual beams, FIBs, as well as TEMs. And then some characterization examples like a warpage measurement tool that we may have, which kind of involves more R&D and characterization of devices. Okay, so just to kind of go back to that last slide was, we look at that and look at it almost like a menu of services, but we don't expect our clients to pick and choose those. So we're happy to consult, and providing the information of some of the history and the failure and the sample information, we can help you construct the appropriate plan and analysis. Okay, so let's move on to the next category of questions here. This would be kind of related to some of the non-destructive failure analysis techniques. So we'll start on the left here. So what non-destructive analysis steps do you take before resorting to destructive analysis? And so there's quite a few and varied in many. So Vidhu, would you like to help answer that question?
Sure. So the initial non-destructive steps are a good way to assess if there are any construction or assembly related concerns. Depending on where the sample came from, you might even want to assess if there are signs of contamination, package integrity, mechanical stress. Sometimes we want to verify the failure before any steps that may alter the behavior of the device. So if there's something that might change because of thermal stress, might change because of mechanical stress, we probably want to record that before we do any of those steps. And this may even give us some invaluable insight about the actual failure mechanisms, which may change the direction of the next steps of the investigation.
Great. And this next question is a little bit kind of related, and maybe you can answer that. How do you perform non-destructive failure analysis on overmolded devices / modules?
Sure, yeah. In an overmolded device or like a multi-chip module, there's going to be a lot of interconnects depending on how things are connected, and that means that there are lots of physical interfaces that could be problematic. And so whether it's X-ray imaging, scanning acoustic microscopy, CT scans or reconstructions, curve tracing, time domain reflectometry, there are a lot of great non-destructive techniques to help identify some of these anomalies before we have to kind of decide on how we're going to actually conclusively say what the problem is.
Okay, and our next question is what will we get when running IV curves on signal and power supply pins? And you know, of course, this would be kind of a general question. It could be ICs or systems or board level. But Wenzen, would you like to answer that question?
Yes, sure. Yeah, we do IV curves and to see what is the shape of the curves, and it's very useful for failures like continuity failures or power shorts or pin leakage. So by looking at the IV curve shapes, we can get a good idea what we're looking at. A lot of time we compare with a good unit, all right, then other times we receive defects or rejects all the time from, say, not directly from like ATE tested parts. So the parts pulled off from board and just say, oh, this part failed on the board. So without ATE test results, these IV curves give us actually good indication of, you know, we test the pins of interest and get good idea of how the IV curves look, and then other times that the test spec on the tester might be pretty wide, and on the bench, when you do IV curves, you can set pretty tight spec and see what is the minute difference between the filling pins and the pin of interest and a passing pin. So a lot of time we do say transceiver pin analysis. We can catch very subtle filling pins that's caused by ESDs. Yep, thank you.
Great. And as we mentioned, some of this non-destructive electrical characterization work actually we use to precipitate and kind of design the next level. So, you know, is there enough power to run infrared hotspot analysis? And that's the type of, you know, IV characteristics may be able to reveal what techniques may be best used to locate that failure. But the next question is how does the B-scan work on the OCOS? Vidhu, could you address that question?
Sure. Just to be clear, OCOS is a type of C-SAM system. So the typical scanning acoustic microscopy image that people are most accustomed to is a C-mode scan, which is basically an XY plane of the device, on a Cartesian plane, like an XY plane, a lateral or vertical or horizontal plane. A B-scan is basically the opposite. It's an XZ plane, kind of like a vertical plane or like a pseudo cross-section. The concern with B-scans is that you lose part of your signal at each interface. So at each interface, some of your signal gets reflected or some gets transmitted. If you hit an interface that either absorbs or scatters your waveform, everything below those interfaces, you basically lose some data. And so therefore the B-scan will get impacted. It's kind of like a pseudo 3D image based on just a top-down optical image. Like you get those curtaining effects from things where your line of sight is broken. So similar kind of problem with B-scans.
And here's another CSAM question. What is the crack size limitation for detectability regarding CSAM? Is there any other non-destructive analysis tool available? Vidhu?
Yeah, this is a good question. This actually comes up a lot. So CSAM can actually detect submicron DLAM or voiding in the Z direction. The primary limitation is actually the spatial resolution of the transducer. So, you know, as some of you guys might be familiar, the lower frequencies transducers can penetrate very deep, but the spatial resolution isn't as good. The higher frequency ones are much better spatial resolution, but you can't, you know, get to the interface of interest because it's a little buried in your package or device. And so therefore the XY footprint of the delaminated area is actually the most critical variable for being able to non-destructively detect it. There are other techniques, you know, based on what the materials are, what we're looking through. Is it like going through the backside of the die? If there's like sample prep processes to enable other creative approaches. So there are definitely a lot of other non-destructive techniques available to, you know, identify some of these cracks. But maybe that's more of a case by case. So if the requester of this question has a specific problem that they're challenged with, maybe we can discuss more offline.
Great. And Vidhu, here's some, I think you spoke to some of these non-destructive analysis techniques. Maybe you want to kind of go through some of these images.
Sure, yeah, these are a lot of good example images. So maybe we can go from like left to right here. So that upper left image is a 3D X-ray or CT reconstruction of what I assume is an inductor or a coil. And so it's a great way to see if there are breaks in the coil non-destructively before we have to do any physical analysis. Like sometimes we have to cross section, but we don't know which direction to come in from or how far to go. So this is kind of a great way to know exactly where to target. I guess the image just right of that is a 2D X-ray image of a profile view of a wire bonded device. And you can probably see that there is a wire bond that's actually lifted. And so based on how the molding is, around that bond wire, it actually gives you an idea of when it happened. So if that bond wire is fully encapsulated by the molding, this break most likely happened before encapsulation, which gives you an idea. It's not something that could be done, in the end application or in the field. It's something that happened prior, in assembly. The two images on the lower left are CSAM images. The left one is a wire bonded device, and so you can kind of see the red and yellow areas are signs of delamination within the package. That image just to the right of that is a flip chip, and you can kind of see there's lots of bump-related problems and delam on that entire edge, upper edge. The two plots on the bottom right are more electrical plots. So the one that says TDR, which is the second from the right, is a technique that we use for detecting discontinuity in transmissions or in trace paths. So the idea is that when you send a transmission down a trace path, when it hits a high impedance, there is a part of that transmission that's reflected. And so if we take the time that it takes to come back to the origin, we can kind of detect, based on the trace path and the materials involved, we can kind of estimate how far the break was from our origin. And that gives us an idea of where potential breaks or cracks or opens can be within a package before actually having to do anything destructive, and therefore paves our road to how we want to go about either doing a cross section or P-lapping or whatever the physical analysis steps would be. The right image is simply an IV curve. Is essentially a pin-to-pin kind of curve trace. Gives us an idea of, if there's a short, there's an open. So it's kind of verifying. I think Winston talked a little bit about the IV characteristics and the kind of the benefits of doing it, even though it's not a fully powered test.
Great, thank you. All right, moving on to the next category of questions is fault localization. So we talked about some of the non-destructive analysis techniques and some of the results that we'll use to kind of coordinate this next step of fault localization. And Winston, you and your team in Northern California, kind of in the Bay Area, is a really semiconductor-centric clients there, support a lot of this varied investigations for fault localization. So question for you, when would you use Auberge versus photon emission versus regular IR imaging via a thermal camera? Would you be able to address that?
This is a very good question. We get asked very often because EAG is a service company, right? When you decide, when you suggest to do one versus other, or you have to do all three, there's a cost associated with it. So Auberge stands for optical beam induced resistance change, and so it uses a heating laser. 1.3 micron heating laser to try to heat up your device 1 pixel at a time in a serial mode and try to induce response from the pin you're trying to monitor. Photon emission is basically you're using a camera to detect light that coming from your device in the darkroom condition. Thermal imaging, you're using a thermal camera to look for longer wavelength emission from your device while it's biased. The difference between these three techniques are spatial resolution, detection sensitivity, and also many other factors. Auberge use laser, so if we can get a response from Auberge, the spatial resolution is great, and contrast of imaging is the best. The highest magnification lens, air gap lens, is 100x, and you could use a solid immersion lens. Photon emission also use near infrared lens, or you could use air gap lens, also solid immersion lens. So the spatial resolution is great, but the image contrast is not as good as Auberge. The thermal imaging, the wavelength is greater than 3 microns, so that the resolution of the imaging is not as great. You can say it's around 3 micron resolution from the air gap lens. So that is the spatial resolution. The sensitivity, Auberge depends on greatly on the sample, right? So using laser to heat up your device. So if you have a lot of top metals that blocking the laser, the laser would not be able to reach deep down to heat up the defect area enough to cause a response. And so that is photon emission has similar issue. You know, if you have a lot of top metal blocking, because the emission coming from the active, from the junction. So if you have many layers of metallization, photon emission analysis has similar issue. Thermal imaging is great that it when you're detecting the longer wavelengths, you're essentially detecting the heat coming from your device. So it depends on the power dissipation. So the heat can permeate to the top, heat up the top of the device, but they require quite a bit power dissipation. So the sensitivity might not be as good as Auberge and photon emission. So there's a lot to talk about these 3 techniques, but I think I have to stop here.
Well, thank you. So next question is, how can we analyze for localized leakage in semiconductors due to ESD or EOS?
I think this question is a little bit related to the first question. So ESD failure tend to have lower level of leakage current. EOS related failure tend to have higher current. So you could, for EOS, when you have higher leakage current, say several hundred microamp or milliamp, you could consider thermal imaging. It's possible to find hotspot. And ESD for current is like sub-microamp. You'll probably have to use Auberge or photon emission, because thermal imaging, there's no, at least now, we're not able to find hotspot if the leakage current is sub-microamp.
Okay, and what tools do you have to locate the failing gate region using external electrical stimuli?
Yeah, this question is not very clear to me, but external stimuli, I think, is talking about the external patterns or external power supplies. What tools? So we could use photon emission analysis to analyze the transistor activities on the device and compare the between the filling unit and a passing unit, see what's the difference. Photon emission is one way. Auberge, sometimes we could use Auberge to analyze functional fail as well. Thermal imaging is when you're using external stimuli to set up your device in the failing mode. If the failing mode is associated with say higher current, say dynamic current, you could use thermal imaging to analyze as well.
Okay, and this last question is, how do you find functional defects in logic chips and flash memory?
Functional defects is we follow similar flow that John explained in the beginning of the presentation, but functional defect might take more techniques and more steps to get to it in terms of fault isolation. But if it's a first design debug, first silicon debug, typically we use photon emission analysis, but it's for functional FA, we have to work very closely with the client to get the setup, the setup ready. so that we can do functional, use the correct test mode to do photon emission analysis comparison. Photon emission is like you're treating the device like a black box. You're comparing failing device with a reference device and see what is the difference. Where is it? Is it the difference? Whether the difference is in the block that you're suspected, and then you zoom in, give you maybe a block or of different size, and then you combine other technique, whether it's you add internal nodes to do microprobing or nanoprobing, or all kinds of voltage contrast combined with D-layer, at a different level. In terms of nanoprobing, you have several techniques. You can use eBig, eBack, or eBirch. So it is a lot more involved and require a service lab work closely with client on this type of problems, functional failures.
Great, thank you very much. And so this next slide just kind of has some basic images here just to show visually kind of what the fault localization imaging looks like. The two colorful ones on the left and the bottom there. The bottom image actually is of a board. So we do have infrared microscopes that have large field of view enough to do board level type of investigation. So you see a QFP and a BGA device right next to each other, looking at the thermography and the temperature range. And on the right side image is a black and white image. That's a infrared backside illuminated image looking through the silicon. And so not only can you use some of these techniques as a direct look at to localize a specific pinpoint failure, but it can also be an inspection tool. So in this case, you could see a large diagonal running crack through the backside of the silicon, which actually was not visible optically on the silicon. Okay, so we're moving on to the next category of questions, and root cause. So there was actually quite a number of questions related to ESD and EOS. And so this theme we try to capture in this slide here. And the first question is how to find the source of electrical overstress that causes failed electronic components. Vidhu, would you like to help answer that question?
Sure. So fully understanding an EOS signature can be a little challenging. So it involves understanding all the potential sources, both internal and external. So the question kind of nails it. How do you find the source? So it'll take some understanding of the magnitude of energy that's in the damage site. So it might take some design feedback or reverse engineering to fully understand the application, how it normally operates, what are the environmental variables in the application and how it was tested, the sequence of events up to the failure. Ideally simulating the actual failure, like if you have like a working hypothesis, let's say you simulate it and you replicate the same damage signature, that's actually the best way to verify the true source. And so there are lots of steps in the process to kind of get to that point.
Okay, and then a similar kind of a theme question. How can we dig deeper into regards to ESD damaged device? How certain is the root cause is ESD? Saying that it's ESD is not very helpful.
Yeah, so ESD is generally a more subtle amount of damage than an EOS event. ESD is, so there are also different things about EOS and ESD. ESD kind of depends on the source is limited, right? Because it's just the initial strike based on the capacitance of whatever it was discharging into or out of your device. The ESD damage may be even overshadowed by subsequent biasing, so that makes it even more complicated to reverse engineer. The best way to kind of analyze it is if you have a sample that has minimal subsequent biasing, or if it just came from an ESD test, like a very specific ESD test, it failed a specific way. We do investigate the damage, and then we kind of have a good idea of what broke and why. Performing the ESD test or latch up or any of the testing. So we also have a test called transmission line pulsing, which kind of characterizes how ESC diodes and other structures react to ESC pulses or transients in general. So that's actually a good way to characterize some of the ESD related concerns.
Okay, and then another similar train of question. We typically get a FA report from IC vendor saying EOS or ESD. How should we get to the root cause of the so-called EOS ESD?
Yeah, so root cause means different things to different people. And so, sometimes it's related to what their role is in the, whatever the situation might be. So we discussed the differences between EOS and ESD in these last two questions. And so, generally speaking, EOS is a little bit more catastrophic. There's a lot more damage because the source might not be as limited as ESD. ESD is a little bit more subtle. ESD is based on pathing. So you basically need a path, from your source to the damage site. So it wouldn't make sense if there was no path at all. So most of the time, it's something that's externally accessible. And then the speed of the ESD strike matters too, how fast it can go and how far into your device it can go. So there are lots of little nuances that we can kind of analyze and then therefore replicate during an ESD test. EOS is generally more longer kind of stuff. Oh yeah, this is actually a good slide that kind of has quite a few bullet points that fall into two separate camps. And so ideally, if you have a working theory for one or the other, we'd want to build a simulation where we can test, if we introduce a transient or, inadvertently change a variable that leads to an EOS event, if we can replicate the same amount of damage. That's a great way to kind of verify your hypothesis. If it's an ESD, we have an entire ESD department with multiple sites to help, kind of replicate some of that on the different types of ESD testing, latch-up testing, and then also the TLP characterization to see if your ESD diodes are actually doing what you think they're doing. Especially if you don't have like a standard cell library kind of device. It's also possible that it's a combination of things, like, something happens and then that leads to a latch up, and then therefore now you're kind of analyzing the like subsequent damage. So it gets a little convoluted. And so having a good handle on it from both the damage aspect and also the potential pathways and potential sources is a good way to kind of attack it from both ends. Okay, great. Well, thank you. And so, yeah, there's a lot of differentiation here, and some of them are kind of get to with or trying to replicate the failure, and that's usually the best way to confirm an ESD type of an event or an EOS event. All right, so next category of questions are a little bit more specific and kind of practical use type of questions. So we'll start on the left-hand side. What are the best options for rapid delayering of chips? So this question is related to the actual ICs themselves, the bare died and deprocessing the process technology. So there's actually not a great specific answer to this, other than the fact that it has a lot of different factors that you have to understand, and so one of them would be the technology node. So you have aluminum unplanarized processes, which are kind of old, and now the newer processes are copper dual damascene and CMP planarized, and now some of the more advancing node technology stuff is the FinFETs and the low-K dielectric. So knowing the type of sample that we have is important. And also the other factors would be how localized and pinpoint is the site that we're going after. So obviously the processing is a PFA or a physical analysis technique. And so to be able to look at a very pinpoint site, let's say through something that's been isolated with infrared microscopy or OBERT, then we have a very specific location to deprocess and look for the physical damage or defect in that area. Now, if we have kind of a non-specific area, maybe a block of circuitry that's during the deprocessing, it may be difficult to maintain the uniformity and planarization that's needed to look at a larger surface area at each layer as we remove the process layers.
And that's kind of like almost needle in a haystack look, if you will, with hundreds of transistors rather than just a group of transistors. So that'll improve our success rate if we have a smaller area to focus. Some of the techniques that we use for delayering may be mechanical parallel lapping or just polishing and removing the layers physically. And then there's a chemical approach, etching copper or aluminum, and the endpoint would be the dielectric in between. And then the plasma reactive ion etching we could utilize as well to remove certain ILDs and dielectric materials. So in a process, we may use a combination or all three to remove each layer selectively for an inspection. Now, some of the advanced node technology things like the FinFETs and things that are lower than 10 nanometer type of technology, the layers are in nanometer thick. So it may be impractical for us to do a really great layer by layer deprocessing. And so that may require something like a plasma fib or a PFib to perform that deprocessing. So in a sense, the speed at which we utilize these techniques would be, how pinpoint is it, what kind of technology is it, and what layer do we think it is, and how wide of an area do we need to inspect. The next question is what analysis can you do to characterize time-dependent dielectric breakdown, TDDB? Vidhu, would you like to answer that?
Sure. Yeah. So this is a very specific kind of technique. It's generally requested by fabs. So to give you guys some background here, when they process transistors or MIM or MOM caps within a wafer, they'll also make other structures in their test areas, like the test structures on the wafer line scribe lines. And in those scribe lines, they'll make basically the caps at the same time as they make all the gate oxide and all the MIM and MOM caps. And therefore, we'll do the testing on the scribe line structures, and that'll give them some confidence in the actual construction of the wafer and the quadrants or however they dissect up the wafer. And so the goal here is there's different types of TDDB testing. One is where you aggressively step up the voltage until failure. And then the other is where you have long settling times and you let it stay biased at certain voltages up to, and you slowly step it up. So one is kind of the time dependent breakdown and one is more of the voltage dependent breakdown. And so after it actually does break down, we'll do physical analysis and we'll kind of understand why it failed and where it failed. And then that'll give them some confidence that their fab process was actually, it met their acceptance data. And so it's generally mostly requested by the fabs, but we can do it in other scenarios. So we can talk about that case to case.
Great. All right. Next question is determining degradation modes that do not result in all-out failures. For example, moderate performance drops that stabilize. Yeah, these would be challenging, kind of the intermittent or not so hard failures. Vidhu, would you like to help answer that as well?
Sure. Yeah. So yeah, this is probably one of the more challenging types of FAs to approach. If it doesn't catastrophically fail or you can't reproduce it reliably, it doesn't have a clear signature, you don't see it on an external pin. Yeah, it just kind of falls into the functional, the memory, speed. There are lots of different variables in a device that can, kind of mitigate or not mitigate, but to affect the performance. And so therefore we kind of need to build the whole story from all sides. And so we have to understand, what's the history. And that's why we ask a lot of those questions at the very beginning, because it kind of gives us some insight about what the potential things that could have gone wrong is. If it can be a fab process defect, if it's something in the application, is it process variation? Is it part-to-part variation? And so ideally, we want to first identify the best way to replicate the failure so that we have something to chase. And that replication might not be very consistent, it might not last very long. But if we can replicate it first, then now we start understanding, okay, is there other environmental variables involved? Did it need temperature, humidity, vibration, radiation, mechanical stress, whatever the environmental variable? Did it need another variable to actually go into that failure mode? Is it like right on the threshold where sometimes it fails, sometimes it doesn't? Maybe we can make it worse so that it's easier to diagnose, and then therefore now we know what the problem is. So there are lots of angles to kind of approach it. If it is like deeply functional in nature and it doesn't need like some sort of crazy environmental variable like radiation, maybe we can utilize other techniques like the laser voltage probe. Maybe SIB circuit edit will put down pads so that we can internally or access internal nodes within the device. And then during operation, we can see how things are toggling inside. Like, is the clock actually toggling at the correct frequency? Does it dip out sometimes? Is there anomaly that happens every 23 microseconds? Things like that. And so that might actually be like a more involved iterative approach where we catch a data point. Based on the data point, we might want to look in 3 other places. And then therefore we kind of branch out until we can kind of get a good handle on what's happening. So yeah, it's definitely a more involved iterative kind of approach.
All right, thank you, Vidu. Our next question is, what is your primary microsectioning method for laminate flip chip packages, diamond lapping film versus silicon carbide versus other? So this would be a PFA or physical analysis question. And I don't believe we have a primary method, but understanding the actual sample and the construction is the main factor in how we approach the cross-sectioning. So again, the materials, what are the materials that we're removing and polishing into, and also the location and the size and the type of failure mechanism that we're trying to find. And so all of those kind of factor into this this method. So a silicon, so a flip chip with let's say a silicon die, we definitely want to start with a diamond lapping film rather than a silicon carbide. Typically, the silicon carbide is a more coarse and rough, and it's great at removing material quickly, but it's also great at cracking and chipping out dies. So these artifacts that may be induced during the physical analysis process, we need to be aware of, and so targeting location. So if we have a laminate flip chip with the FR4 multi-layer kind of a material board, then is the failure that we're looking at, is it on the die process layers, or is it actually in the laminate packaging? So if it's in the laminate packaging, we may be a little bit more aggressive in using things that may remove a lot of material to get to that location of interest. But again, we will go through a series of polishing steps from finer grit into potentially using aluminum oxide and some of the diamond slurry suspension, and try to utilize those finer techniques to get the best imaging of the failure mechanism. Now, the artifacts are things that, again, we really need to be aware of. Are we inducing or embedding like the silicon carbide particles into the sample itself and may confuse or obscure some of the analytical work? Now, the different types of cross-sectioning methods that we have, obviously the metallurgical cross-sectioning that involves the film and the silicon carbide and grinding, but that does introduce a lot of artifacts like delamination, cracking, and things. So other techniques that we utilize to help supplement or to mitigate some of those is to use ion mill, broad beam ion milling, as well as dual beam fib, which is going to be a little bit more precision based, and a plasma fib, which can be another ion based cross-sectioning, but in a larger scale. So let's see, if we go to the next slide, we have a few pictures here that kind of show some of the things that I talked about. So looking at the very left image is a FR4 copper stack via, and it was done with a metallurgical, mechanical cross-section. But this crack there in the via wasn't actually visualized until we cleaned it up or removed the smearing artifact. So copper, as you know, is softer material, and so when you're doing this polishing and grinding, it backfills the crack and it smears across the crack, so that it may actually prevent you from visually seeing this crack. But on this particular analysis, we likely performed, maybe some of the non-destructive initial investigation steps like scanning acoustic microscopy to make sure that there isn't like large gross internal delamination within the board, and then maybe an X-ray to see that there's no missing vias or something significant of the construction nature. And maybe through TDR, we know that there's a open here within this via stack. And so by cross-sectioning and maybe doing an ion mill to clean up some of the smearing artifacts, we were able to locate the fine crack. And again, it could be an ion mill. It could also be a chemical delineation etching to create topology for some of the more SEM or electron imaging-based tools. This on the bottom row of images, the center one is of a copper pillar interconnect on a flip chip, and that was done using a dual beam fib. And the advantage of obviously a dual beam fib is you can have use GDS navigation and target exactly the location that you want to hit, as well as being able to do that with no mechanical kind of stress and artifacts. The right side image there is a kind of a colorful image. It's using cross-section using a fluorescent dye penetrant chemical, and that's used to kind of look at the crack propagation. And so you could see that the fluorescent dye lights up in UV and locates all of those cracks better than just looking at this one plane. Okay. So we're kind of at the last category of questions here, and this one's kind of looking at current and future challenges and complexities. So the first question: are newer electronic devices becoming less resilient, and is it hard to diagnose issues on these smaller components? Vidhu, could you help answer that question?
Sure. So I think it's more of a compounded problem. I think the various industries are pushing the boundaries of technology in general, but also trying to achieve it in the smallest footprint possible. And so now we have electronics and things that we've never had before. So now some of those, device manufacturers and integrators have to consider environmental variables that they've never had to consider before. So there's all of these other, options, or not options, but possibilities that were never, kind of a concern before. And so it's definitely harder to diagnose concerns on smaller, more compact kind of components. If you're kind of jamming a lot, like 10 dies into the same module, it's definitely harder to distinguish, where the failure is and which dies actually play a role in the failure. So there's very buried connections. But to be honest, the community has come a long way too. We've come up with lots of innovative approaches. Despite all of these challenges, like very high frequencies and like little components where everything matters, like all the little nuances of the setup will influence the frequency of traces and trace paths. Despite all of these challenges, the community continues to push forward with like novel and innovative solutions to help solve the problems of tomorrow.
Great. And I know we're in the interest of time, we'll probably try to tackle these questions real quick because we do want to take some online questions as well. So next question is, what are the current and future primary challenges present in the failure analysis techniques? Wenzel?
Yeah, I think Vidhu just touched upon that. I think what we're seeing, the challenge we're seeing is still the complex packaging, the integration of components on all the same die, SOC, and also the nodes, ever decreasing node, process node, and those are the primary challenges. And then the push for smaller, better resolution, better sensitivity. For example, that the TDRs in the terahertz territory, the CSAMs in the gigahertz territory, the SCM, the TMs, even challenging, to see those small node, 3 nano or 2 nanometer or 1 nanometer coming along the way, and also the new designs and new process. And I've seen and different designs and the laser and discrete components and yeah, so it's just challenges from more direction, or new applications, medical devices, and requires we do analysis in the cryo mode, you know, more precision cuts, but big cuts. Say mechanical cross section not be able to target anymore, so you have to use FIB to target. For EFAs, right? You do isolate fault while the device is running. How do you handle several hundred watt? How do you do cooling? All these are current and future challenges, but we are still hopeful that we're working on this interesting field.
Yeah. And the next question is kind of, you know, what are some of the measures that EAG is taking to address some of these challenges? And you know, our customers are the mouthpiece, and we listen to our customers and what their needs are and what their future plans are. And we also kind of invest some time looking at the trade shows and some of the emerging technologies and techniques that are out there. Our marketing and commercial team do a great job of exploring different techniques and services and things that we should consider. Vendor partnerships are things that we are always looking at, you know, these emerging technologies, exploring new techniques and trying to make those techniques available to our clients. And the last question here, and Wenzen, I'll ask it, and then maybe I'll start scrolling through some of the next slides here. What techniques do you see driving business growth in the next few years, and where is the industry moving?
I just give a few examples. Say sample prep, right? For complex packaging, we have to get to those, you know, remove the sample, be able to test them. So sample prep, and yeah, we just purchased this new Allied high-tech prep tool to help us handle the challenging sample prep, and how to handle the small node. Yeah, those plasma delayer. Plasma FIB delayer is one direction, and nanoprobing, you know, those. So yeah, where's the industry is moving? We've seen a new materials from quantum computing stuff. So all directions.
Yeah, and quickly, you know, and I think you touched on some nanoprobing techniques, and obviously we offer that service as well. You know, some of the smaller node technology things needs a solid immersion lens imaging. It's a little bit higher resolution imaging than the traditional air gap, and some of the techniques like warpage deformation measurements that we can offer. So I know we ran through some of those really quickly, but if any of them are interesting to you or you have interest in learning more, please contact us about them. And Dan, I don't know if we have any quick questions that we can answer. I think we just have a few minutes here left.
Yeah, I think we can answer one or two quick questions. There were two that came in that were very interesting. One asked about the pros and cons of decapsulating a package with laser ablation. I don't know if you can address that one real quick.
Pros and cons with laser. Well, the pros is that we can actually open up a very specific areas more precisely. And you know, some of these packages that have you know, copper bond wire, things like that are more susceptible for over etching using traditional decapsulation methods. It's an advantage to have that molding compound removed before the chemical application. But you know, some of the disadvantages, if you go too far, you can actually damage the die. That's a big issue if you're not aware of how deep things are.
That's pretty clear, John. So I just have one last one. This is an easy one. So how can people send in an FA job to us? If you give a quickie on that.
Wow. Well, definitely. I mean, there's various ways. Through the website is a good one. If you see, go to our website and look at some of the techniques that are of interest to you. There's a little entry for inquiries. You can contact us directly. We would be happy to talk to you over a phone call or a Teams meeting. There's our a really great commercial team that does a lot of triage, handling of initial conversations, and the old method of phone call. We are open, and we are really excited to help any customer that we can.
All right, thank you very much, John. I think that wraps it up. Vivian, I think we had to go to the next slide. Oh, I just wanted to say quickly about EAG. We have 26 different sites now. Confidentially is core to our business. We have secured servers. We have strict rules on who can work on your samples, who can see your samples, who gets your data, and how we send that information back to you through secured FTP or secured emails. We have many, many sites and many, many samples. We're happy to talk to you about all of them. So please, keep in mind you can reach out to us, as John mentioned. Next slide. And this is where Vivian's going to tell you about our next cool stuff that's coming up. Vivian?
Yep. I just want to say thank you to all of our experts for this great discussion and presentation, and thank you to everyone for attending today's event. If we didn't get to your questions today, we will be following up with you soon. If you have any other questions, please send in your questions to the email address on the screen. That's customerservice@eurofinseag.com. I also wanted to mention that I've added a few links to some of our resources in the chat window, along with a link to our webinar library, where you can view our past webinars or register for upcoming ones, which you can see on the slide. I've also added a link to our next Ask the Expert webinar that's happening next week. Once you leave today's webinar, you'll receive a survey on the presentation, and we would greatly appreciate your feedback. On behalf of Eurofins EAG Laboratories and our experts, thank you for joining us, and have a great rest of your day.